In this video, we're going to be looking at our Chapter 5 exam review. So let's get started by looking at evaluating some integrals. So for number 1, we're just going to apply the rule if we have an integral in the form of x to the n. We know the antiderivative is going to be x to the n plus 1 all over n plus 1 plus some constant of integration. So for this antiderivative, we're going to apply that rule. So we would have x to the negative 2 plus 1 all over negative 2 plus 1 plus our constant of integration, which is x to the negative 1 all over negative 1 plus c. And we could simplify this as negative 1 all but this one is a definite integral, so we're going to have to apply the fundamental theorem. And the fundamental theorem states that if we have an integral, we need to find the antiderivative evaluated at b minus the antiderivative evaluated at a. So the antiderivative of 1 with respect to y would be y plus 3y squared over 2 minus y cubed over 3. And we'll evaluate this from 0 to 4. So this is equivalent to 4 plus 3 times 4 squared over 2 minus 4 cubed over 3. And then we have to subtract off. We just did our f of b. Now we have to subtract off the antiderivative evaluated at the lower limit of integration. So we'd have 0 plus 3 times 0 squared over 2 minus 0 cubed over 3. And we can see this whole piece goes to 0. So we have 4 plus, now 4 squared is 16 times 3 is 48 divided by 2. And then we have 4 cubed, 64 divided by 3. And if we get a common denominator, now we would have to multiply each one of these by 3, so we'd have 64 over 3. And so we would have 84 minus 64 all over 3. Number 3, we can rewrite this as 3 times the integral from negative 1 to 1 of 1 over t dt. And we know the antiderivative of 1 over t is ln of the absolute value of t. And we'll evaluate this from negative 1 to 1. So we would have 3 times ln of the absolute value of 1 minus the ln of the absolute value of negative 1. And the ln of 1 is 0. So the ln of the absolute value of negative 1 is 0. So we would have 3 times 0. Number 4, we're going to find the antiderivative of cosine of theta, which would be sine of theta. And we're going to evaluate this from 2 to 2x. So we would have the sine of 2x minus the sine of 2. And that's the exact value. I'm not going to change that to its decimal approximation. This integral, we need to recognize that we have 1 all over the square root of 1 minus x squared, which is the sine inverse of x. That's the antiderivative of this. So we're going to evaluate this from 0 to 1/2. So we'd have the sine inverse of 1/2 minus the sine inverse of 0. And the way to think about the sine inverse of 1/2 is, let me do a little aside here. If we have the sine of an angle equals some number, if we look at the sine inverse, we're looking at the sine inverse of a number that equals an angle. So if we wanted to look at the sine inverse of 1/2 equals an angle, we could write it and say the sine of some angle equals a number 1/2. And then we can think about that and say, well, the sine of pi by 6 we know is 1/2. And then the sine inverse of 0 is 0. And the sine inverse is restricted between negative pi by 2 and pi by 2. So we only pick up pi by 6. Number 6, we have, it looks like a u substitution problem. So if we let u equal 2x minus 3, du would equal 2 dx. Now, if we're going to make our replacements over here, we can see that we'd have u squared in the denominator, and then to replace dx, we're going to divide by 2. And that's what dx is replaced by, du over 2. And so we have 1 all over u squared du over 2. Now we could rewrite this as 1/2, bringing this 1/2 out front, times the integral of 1 all over u squared du. So we have 1/2, and I'm going to rewrite my integral as u to the negative 2 du. Now I'm going to apply our rule, and so we would have the antiderivative would be u to the negative 2 plus 1 all over negative 2 plus 1, which equals 1/2 u to the negative 1/2 all over negative 1. So if we simplify that a little bit, we get negative 1/2 times 1 over u. And now I'm going to change everything back into terms of x. So u, we said u is 2x minus 3, so we'd have 2x minus 3, and we're going to evaluate this from 0 to 2. So we have negative 1/2. So first we're going to plug in 2 for our x here. So we'd have 2 times 2 is 4, minus 3 is 1, minus, now we plug in 0. So we'd have 1 all over 2 times 0. So that would just leave us and if we simplified this, we have 1 plus 1/3, which gives us negative 1/2 times 4/3. And if we simplified that, we get negative 2/3. Okay, we have another definite integral, and it appears we need to use u substitution again. So I'll let u be this function, the inside function. And so we would have 2 dx. And when we're making our replacements here, we can see that we'd have square root of u in the denominator. And we don't need this 2, so we'll divide that. So we'd have du divided by 2 equals our dx. And so I'm going to bring the 1/2 out front, du. Now we haven't replaced our x, and so we'll look at this relationship to solve for x. So we'd have 1 minus u divided by 2 equals x. So we have u minus 1 all over 2. If we invert and multiply, we would get u minus 1, and then we'd have 2 times the square root of u du. And so I can bring this 2 out front also, this 1/2. So we would have u minus 1 divided by the square root of u du. And let's divide each term in the numerator by the square root of u. So this would simplify now. U to the 1/2 minus u to the negative 1/2. So now we can find the antiderivative. So moving up here, we would have 1/4. Now we're going to add 1 to the exponent, and we would have u to the 3/2 divided by 3/2, but I'm going to invert and multiply, minus, now again we're going to add 1 to our exponent, so we would get 1/2, and if we divide it by 1/2, it's the same as multiplying by 2. Now let's change this back into terms of x, and remember we have to distribute this 1/4 through, so let's reduce. So we would have 1/6. U is back up here, 1 plus 2x to the 3/2 minus, now the 1/4 times 2 would leave a 1/2, and then 1 plus 2x to the 1/2, and now we can write our limits of integration, 0 to 4. So we would have 1/6. Now we're going to substitute in 4 for our x's. So for here, we'd have 8 plus 1 is 9 to the 3/2 minus 1/2. Now we're going to substitute in our 4 here. So we'd have, again, 9 to the 1/2. Now we're going to plug in 0. So we'd have 1/6. And when we plug in 0, we'd have 1 to the 3/2, and then minus 1/2, and 1 to the 1/2. So 9 to the 3/2, square root of 9 is 3, cubed is 27, so we get 27 over 6, minus square root of 9 is 3, so we get 3/2, minus, so the square root of 1 cubed is still 1, so we'd have minus 1/6, and then we'd have plus, because this negative needs to be multiplied through, so we'd have plus 1/2. So if we changed everything into sixths, we'd have 9/6 minus 1/6 plus 3/6. So it appears we have 17 plus 20 over 6. Okay. Let's erase that and leave enough room for the next problem. So here we would let, again, u equal x minus 1. It's a u substitution problem. So du equals dx. So if we made our replacements at this point, we would have the square root of u du. But we have not replaced this x. So we will solve for x here. So we'd have u plus 1 equals x. So we will write that in here. So we'd have u plus 1. And let's multiply the square root through. So we'd have u to the 3/2 plus u to the 1/2 du. Now we can take our antiderivative. So we're going to be adding 1 to our exponent to get u to the 5/2, and that's divided by 5/2, or multiplying by 2/5, plus, so we'd have u to the 3/2 divided by 3/2, or multiplied by 2/3. Making our replacements back to terms of x, we would have u equals x minus 1 to the 5/2 plus 2/3 x minus 1 to the 3/2. And now we can evaluate this from 1 to 2. So 2/5, 2 minus 1 to the 5/2 plus 2/3, 2 minus 1 to the 3/2 minus, now we're going to evaluate it at 1. So we'd have 2/5. Now here we'd get 1 minus 1, which is 0, so that goes to 0. And plus 2/3, and again this goes to 0, this quantity goes to 0. So this whole piece goes to 0. So we're left with 2/5 times 1 to the 5/2 plus 2/3, 1 to the 3/2. So that leaves us 2/5 plus 2/3. And if we get our common denominator of 15, we would have 6 plus 10. So we would have 16/15. For number 9, it's a u substitution problem. So let's let u equal ln of x, and du then would be 1 over x dx. So when we make our replacements, we're going to have the cosine of ln of x, which is u. Now we still have to replace 1 over x dx. That's replaced with du. Oops, so I have cosine of u du. The antiderivative of cosine of u would be the sine of u, and then we have our constant of integration, and then we'll substitute u is ln of x, and there's our antiderivative. For number 10, let's divide each term by x squared. So we'd have x divided by x squared and minus x squared divided by x squared. So rewriting this in the form of x to the n, This one we won't, because we can see it would be x to the negative 1, which is 1 over x, and we know that's the special case. So now we can apply our rule. We're going to add 1 to the exponent and divide by the same power. We know that the antiderivative of 1 over x is the natural log of the absolute value of x minus x, and then plus our constant of integration. This is an indefinite integral. So we'd have negative 1 over x plus ln the absolute value of x minus x plus c. So there's our antiderivative. Number 11 is another u substitution problem. We let u equal negative 5x du and equals negative 5 dx. So making our replacements, we would have e to the u. Now to replace dx, we're going to divide du by negative 5. So I'm going to bring that negative 1/5 out front. So we have e to the u du. Now the antiderivative of e to the u is e to the u. Now changing this back into terms of x, we would have e to the negative 5x, and we're going to evaluate this from negative 2 to 2. So we have negative 1/5 e. Now when we plug in 2 for x, we would get negative 10 minus, now we're going to evaluate it at negative 2, and we would get positive 10. And I'm going to leave it as the exact value. Number 12, if we let u equal cosine of x, du would equal negative sine x dx. And I can see we don't need the negative, so let's divide that. So replacing, we have the cosine of u would replace this piece right here in terms of u. Now we need to still replace the cosine of x and dx. I'm sorry, the sine of x dx. And the sine of x dx can be replaced with negative du. And I'm going to pull the negative out front. So the antiderivative of cosine of u is the sine of u plus our constant of integration. And then we would have the negative sine, and we're going to replace u with cosine of x. And there's our antiderivative. Okay, number 13, find the area under the curve of x squared plus 1 on the interval from 1 to 3 with n equals 8. So that means we're going to break this up into 8 subintervals, or 8 rectangles. So the idea is, here we have our function. Let's say this is x squared plus 1. And let's say this is, let me give myself a little bit more room. Let's say this is 1 here. We're trying to find the area of the curve from 1 to 3. Now, we know the width of each rectangle would be b minus a, all divided by n. So 2 over 8, 1/4. And we know we're going to start our x sub I. We're going to start at 1 plus our delta x times I. So if you wanted to set up the Riemann sum for this, it would look like this, which would give us our Riemann sum, and it would be f of x sub I, which is 1 plus I over 4 times our delta x, which is 1/4. Now, if you wanted to use the Riemann sum, we know the 1/4, the width, is going to stay the same, and we can bring that out front. So we would have 1/4. And then looking at this graphically also, I just want you to see it visually also. What we're doing here, we're finding the area of this rectangle. Now we're starting at 1, and we know the width is 1/4, so this would have this value right here that we plug into the function to get the height of the rectangle would be 1 1/4 or 5/4. And you can see, using our Riemann sum, if we plugged in 1 for I down here in our Riemann sum, we'd get 1 plus 1/4, which gives us that value to plug into our function. So we would get our 5/4. Now, if we plug 5/4 into our function, it would be 5/4 squared plus 1. That would be the area of the first rectangle. Now the second rectangle. We know the width is 1/4, so we would be adding 1/4 to our to this value right here, which we said is 5/4. So if we went back to our Riemann sum, we know we would have 1/4 times, if we plug 2 in, we'd have 1 plus 2 over 4, which is 1 1/2. And we know that 1 plus 1/2 is just 3/2. So we would have 3/2 squared plus 1. And that would give us the area of this second rectangle. And you can see, if we added our 1/4 to get this value of x here, we have 6/4, which is 3/2. So you can see how the Riemann sum finds these values for us if we set this up correctly. Now the next value we would plug in to find the area of the third rectangle, we would have plus 1/4. And this value now, we would be adding 1/4 to our 3/2. But I'm going to go back down here to our Riemann sum. And let's use that to find our value. So plugging in, now we're at the third rectangle. So we would be plugging in I equals 3. So we would get f of 1 plus 3 over 4. That's the value we're going to plug into our function to get the height of the third rectangle. Now we can see that's 7/4. So we'd have 7/4 squared plus 1. That's the area of this rectangle. And then let's say this is our our fourth rectangle. And now if we plug in 4 to I, you can see we would get 1 plus 1, which is 2. And you can see that's where we're at. To get the height of the fourth rectangle, we would plug 2 into our function. So we'd have plus 1/4 times, and we said we have 2 squared plus 1. So there's the area of the fourth rectangle. Now we still have 4 more rectangles. So we would have plus, and we know the width's going to be 1/4. And if we went back to our Riemann sum, we'd be plugging in 5. So we'd have 1 plus 5/4, 1 5/4, which is 9/4. So we would have 9/4 squared plus 1. The next rectangle, the 6th rectangle, we'd have 1 plus 6/4. And that's going to be what we're plugging into the function now. So we would have 10/4. Let's see. Plus 1. And then that was our 6th rectangle. Now we're at 7, so we're going to plug in 7. So we would have 1 and 7/4. So that would be then our last rectangle. We're going to plug in 8. So we'd have 1 plus 8/4, and that's just going to be 1 plus 2, and that's where we end up for our last rectangle. Now if you went through and did all these calculations, you could have factored the 1/4 out, and then you could just add all the ones together and then square each one of these terms. I believe you will get something around 10.93, I believe, if you go through and add all of that up. Okay, problem number 14 wants us to find the area under the curve from the previous problem. Now let's write down, we had our function, which was, what is it, x squared plus 1, and we're trying to find the area under the curve from 1 to 3. So when we're finding using a Riemann sum and letting the number of rectangles be n, then we're going to take the limit as n goes to infinity. We're finding the exact area under the curve. So we need to find these three things. First of all, delta x. We know that is going to be b minus a all over n. So that's the width of each rectangle. X sub I is a plus delta xi. So this would be our x sub I. And then you just need to know that we're going to take the limit as n goes to infinity from I equals 1 to n of f of x sub I times our delta x. So this is all the information we need. We need these two pieces of information to plug into this now. Once we plug that in, we'll be able to find the exact area under the curve. So this, we have I equals 1 to n, and our x sub I is 1 plus 2i over n. And delta x is just 2 over n. So if we actually plug that into the function, our function is x squared, so we're going to plug in 1 plus 2i over n squared plus 1. That's plugging in our x sub I to the function, times the 2 over n, which is our widths. Now when we're working with a problem like this, I think it's easiest, we're going to multiply this out first and then separate each term with its own summation. And I think that makes these problems easiest, these types of problems. So we have the limit of n goes to infinity, I equals 1 to n. And then let's multiply this out. We have 1 plus 2i over n squared would be 1 plus 4i over n plus 4i squared all over n squared. Now the 2 over n, when I goes from 1 to n, this 2 over n does not have an I in it, so that will not be changing. So we could consider that a constant. So we could actually bring that out front of our summation notation. So let's separate each one of these with its own summation symbol. And that's where I said this, I believe, makes these problems easier to work with if you write it like this. Takes a little bit more work, but tend to make less errors if we do it this way, I think. So now where am I here? Summation from I equals 1 to n, and we would have 4I over n, and then plus the limit as n goes to infinity, summation from I equals 1 to n, and we have 4I squared over n squared. Now I see that I forgot our plus 1 here. So when we expanded that, we should have had a plus 1 here. So this would actually be 2, because I'm going to combine this and this together, so we'd have 2 right there. Now let's look at this piece right here. If we're summing up 2 from 1 to n, that means it's 2 plus 2 plus 2 plus 2 n times. So we would, if we take the limit of the summation of 2 from I equals 1 to n, that's going to be 2 plus 2 plus 2 n times, or 2 times n. Just this summation. And then we still need to take the limit as n goes to infinity of this term, plus. Now, over here with the next term, what we're trying to do here is get I by itself in front of the summation notation. So let's bring out this 4 over n and multiply it by our 2 over n. So we'd have 8 over n squared. And then we have our summation from I equals 1 to n of I. And same thing with this one. We're going to pull out, we want to isolate that I squared. So we're going to multiply 2 times 4 and then n squared times n. So we'd have n cubed, and then the summation from I equals 1 to n of I squared. The reason we did that is we know this equals something in terms of n only. And the same thing with this one here. We can rewrite this one now in terms of n only. And then we can find the limit as n goes to infinity. So before we get there, let's just finish this term. The limit of 4 as n goes to infinity. So that one we can find. Now this one, we know that we can replace this summation with n times n plus 1 all over 2. And this one we can replace with n times n plus 1 times 2n plus 1 all over 6. Now the limit of 4 as n goes to infinity is 4. Now when we analyze this next limit, I'm going to get all my n's together, and since this is being multiplied together, I can switch these two and rewrite this as 8 over 2 times, and if I multiplied the n in the numerator, I'd have n squared plus n all over n squared. I've gotten all my n's together. Now if I take the limit of n squared plus n all over n squared, I know that is just 1 because my degree is the same in the denominator and numerator, so I just take the coefficients, which would give me 1. If you wanted to use another technique, you could take the limit of that quantity and get infinity over infinity, apply L'Hopital's rule, take the derivative, and so forth. And you see you would get 1 also. So we have 4 plus, and we said that the limit of this quantity here is just 1, so we'd have 1 times 8 over 2, so we'd have 4 here. And I'm going to use the same technique over here. If we take the limit, and I'm going to switch now, the 6 with the n cubed. Now if I multiplied out this quantity up here, we'd have 2n squared plus 3n plus 1 times n. So we would have 2n cubed plus 3n squared plus n all over n cubed. And now we can find the limit of this because we have the degrees are the same, so we take the coefficients, so we would get 2. So we would have 8 over 6 times 2, and that would give us 8/3. So we have plus 8/3. Now if we simplified this, this would be 24/3 plus 8/3, which is 32/3. And comparing that to our previous problem where we took, 8 rectangles and estimated the area under the curve, here we're getting 10 and 10.67, and I believe we got 10.93 in the last problem. And this is an increasing function, so it makes sense that if we're using the right side of the rectangles, we're going to have an overestimate. So 10.9 was a little bit more than our 10.67. Find the function and the interval for the area under the curve. I know that to find delta x, the width, I take b minus a over n, which would be this piece right here. So I know b minus a would be 3. That would be the width of our interval. Now we know that our x sub I equals a plus delta xi, and this is our starting point. So we're starting at -1 and we have a length of 3. So our interval would be from -1 and then it has a length of 3. So 0, 1, 2. That would be the length of our interval. And our x sub I is a, just like we wrote up here, a plus delta xi. So it'd be -1 plus 3i over n. So I'm looking for where have I plugged this into all the x's. Well, I see here this would give me x cubed minus, well, there's another x I would have plugged it into, minus x, and then we had just have a constant. So that would be the function that we're finding the area under the curve on the interval -1 to 2. A ball is thrown upward from a 200-foot building with an initial velocity of 24 feet per second. What is the velocity of the ball as it hits the ground? Since we're working in feet, we know the acceleration is negative 32 feet per second squared. To find velocity, we take the antiderivative of our acceleration. So we'd have negative 32t plus some constant of integration. But it gave us an initial condition. It said the initial velocity equals 24. So when t equals 0, let me write our velocity function down here. We have negative 32t plus c. Now v of 0 would equal 24, and then we're plugging in 0 for our t, so we can solve for c. So c would be 24. So we know our velocity function is negative 32t plus 24. We know to find our position function, we take the antiderivative of our velocity function. So if we take the antiderivative here, we get negative 32t squared over 2 plus 24t plus c. So if we use our initial condition, it says the height of the building is 200. Now we can solve for c. So here I'm just going to simplify this. This would be negative 16t squared plus 24t plus c. Now using our initial condition, we would have 200 equals, this goes to 0, this goes to 0, so c equals 200. So we have our position function. S of t equals negative 16t squared plus 24t plus 200. Now to find how long it took for the ball to hit the ground, we would set our position function equal to 0. T plus 200. And so if this is not factorable, we'd have to use our quadratic formula. Let's see, it appears that 8 could be factored out. So we'd have 2t squared minus 3t minus 25. But that doesn't look like it's going to be factorable. So if we used our quadratic formula, we'd have t. Now the negative 8s can just be divided out. So using the quadratic formula, we'd have negative b plus or minus the square root. B squared would be 9 minus 4 times a times c all over 2 times a. And if we simplify that, we would get 3 plus or minus the square root of 209 all divided by 4. We wouldn't take the negative value. We'd want a negative time. So if we estimated that with a decimal, it would be 4.36 approximately. That's how long it took for the ball to hit the ground. Now to find the velocity when the ball hit the ground, we would go back to our velocity function and we would plug in 4.36 for t. That's when we want to know the velocity. So we'd have negative 32 times 4.36 plus 24. So v of 4.36 would be the velocity of the ball at the instant it hit the ground. So this gives us a negative 115.52, and our units would be feet per second. So it's traveling at 115 feet per second. If oil leaks from a tank at a rate of R of t, gallons per minute at time t, what does this integral represent? Now, if we have an integral of a rate of change, we know this gives us the total change. So what are we looking at the total change of? Well, if oil is leaking from the tank, we're looking at the total rate, the total change, or the total amount in gallons of oil that has leaked from the tank on the interval 0 to 120. So this would represent the total amount of oil in gallons that leaked from the tank and since we're in minutes, we're looking at the interval from 0 to 120. So if that's minutes, it looks like it'd be the total amount leaked in 2 hours on the interval 0 to 120 minutes. Now we're going to use we've learned that if we have this integral, which represents the area so far under the curve, that if we want to take the derivative, well, think about it this way. If we took the antiderivative, we would have the antiderivative evaluated from a to x, which would give us f of x minus f of a. And then if we're going to take the derivative of this now, this is a constant, so that would go to 0. So we would simply have f prime of x, which is just going to be our f of x. Now, if we have an integral where we're going from a to x cubed, let's say, our antiderivative is f of t. We're going to evaluate it from a to x cubed. So we'd have f of x cubed minus f of a. But this is asking us to find the derivative. So if we find the derivative of this, the derivative of the first term would be f prime of x cubed times the derivative of the inside function, since it's a composite function. And this still goes to 0. So think about this rule because we have an x cubed. So let's see how that would work for this problem. So if we have the integral from pi over 2 to x cubed of cosine of t dt, we just saw this should equal our f prime of x cubed. So, and I mean the f prime of x, which is our f of x. So we'd have just the cosine of x cubed. And then we said this has to be multiplied by the derivative of the inside. if this is x cubed here, we would have x cubed times our 3x squared. So times our 3x squared. The position function of a particle is given by this equation. Find the total distance. We know to find total displacement, we just have to find this. The antiderivative of the velocity on the interval. That gives us total displacement, or displacement. Now to find total distance traveled, if the particle changed direction, so say we had, this is our velocity function. Here this would be positive area, but this would be negative area. So that's why for displacement we can just take the antiderivative over the interval, because it will add the positive and subtract the negative and tell us how far we are from our starting point. However, for total distance, this will give us a positive area on the interval A to C, but C to B is negative, so it would be the net area that'd be subtracted off. But we don't want to subtract it off. This is just a different direction. We want to add that into our total distance. So that's why we have to take the absolute value of our velocity to find total distance. So this is our velocity and time graph. So to find the total distance traveled, we're going to take the antiderivative of t cubed minus 6t squared plus 9t minus 2. And we're going to take the absolute value over that interval, which means we could be changing direction, and we need to find if we're changing direction like we did down here. So let's determine if our particle changed directions by taking the velocity function and setting it equal to 0. So our velocity would be the derivative of this function, which would be 3t squared minus 12t plus 9. So if we set this equal to 0, let's factor out a 3. T squared minus 4t plus 3. This would factor, hopefully, into t minus 1, t minus 3. So we have two roots. Let's build a number line. So what's happening on the interval from 0 to 1? So we're going to look at f prime of, let's say, 1/2. If we go back to our velocity function and plug in 1/2, I'm just going to use the factored form. I would have 1/2 minus 1, which is a negative number. 1/2 minus 3 is another negative number. A negative times a negative gives a positive value. So we're moving forward. Here, f prime of, let's take 2. 2 minus 1 is positive. 2 minus 3 is a negative. Negative times a positive is a negative. F prime of 4. 4 minus 1 is positive 3. 4 minus 3 is positive. A positive times a positive is positive. So we're moving forward on this interval, and we're moving back on this interval. So we'd get a negative value, but again, we're moving forward here. We are going to need to check our integral on the interval 0 to 1 of our velocity. We know that's going to be positive value, so we don't need the absolute value of that one. On the interval 1 to 3, we're going to need to take the absolute value, because we can see that would give us a negative value. And then from 3 to 5, this is going to be positive again. So we do not need the absolute value. Our velocity function, we found our velocity. Let me rewrite it up here. Our velocity equals 3t squared minus 12t plus 9. Our antiderivative is t cubed minus 6t squared plus 9t. We're going to evaluate this from 0 to 1. Plus, and then this is going to be the same antiderivative, only we're going to have it in absolute values. We'd have t cubed minus 6t squared plus 9t evaluated from 1 to 3. And then we have our t cubed minus 6t squared plus 9t from 3 to 5. So now we just need to evaluate each one of those integrals, and that would give us the total distance traveled. So we would have 1 minus 6 plus 9, and if we plugged in 0, that would just give us 0, plus, now we're evaluating it at 3, so we would have 3 squared minus 6 times 3 plus 9 times 3 minus, now we would plug in 1, so 1 cubed minus 6 times 1 plus 9 times 1, but then we're going to take the absolute value. And then plus, we would have 3 cubed minus 6 times 3 squared plus, I'm sorry, this is 5, plus 9 times 5 minus, now we're plugging in 3, minus 6 times 3 squared plus 9 times 3. And if we calculate that, we would get, don't have room at the end, so that would give us 28 feet. So that would be our total distance traveled.